Sir, good evening, sir. Good evening to all. I am Dr. A. Maitreyi, Associate Professor, Department of Mathematics, Stanley Engineering College for Women Autonomous. We are honored to welcome Professor Srinivasa Rao Pentyala, a distinguished academic from the Department of Mathematics and Computing at IIT ISM Dhanbad. With a career spanning over 2 decades, Professor Pentyala sir brings a wealth of expertise in scientific computing, numerical methods, and fluid mechanics with impactful applications in numerical weather prediction, heat transfer, and IoT in agriculture management. His academic journey includes prior roles at BITS Pilani and a Tata Research, Development and Design Center. And he holds a PhD from IIT Kanpur, a top-ranked scholar, All India Rank 2 in GATE Mathematics. He has published over 50 peer-reviewed articles, guided a numerous PhD and postgraduate dissertations, and led several nationally funded research projects. Professor Pentyala is not only a prolific researcher, but also a passionate educator and mentor, known for his problem-solving acumen and algorithmic thinking, and dedication to interdisciplinary innovation. Please join me in extending a warm welcome to Professor Pentyala as he shares his insights and expertise with us today. Welcome, sir. You can start, sir, please. Good evening, sir. You can start.
So thank you for So thanks to everyone, and special thanks to the madam for giving the introduction and making the schedule in time and collecting the people from over the globe for accessing in the online mode. In fact, everybody started their academic, the semester started, but she has taken the keen role to organize this ATAL online FDP program, especially in the offline hours, like after 5 o'clock and all. So I think all of us will be very grateful to Madam for taking this such an initiation and interest. Well, my talk would be on sustainable energy and climate change. This is very very important topic, especially for the researchers who are involved in mathematics as well as computer science and also physics and to some extent some atmospheric sciences and so on and so forth. Well, all of you knowing very well, climate change is very very important topic. Especially in agriculture, engineering, and space dynamics, and also the weather prediction is one of the very very important topic. In fact, the government of India has highlighted some of the very core areas, thrust areas. One of the thrust area is the climate change and atmospheric modeling, and out of which the most important thing is the cloud bursting. As we see that the atmospheric or climate change is very versatile. The people who are sitting in the peripheral area of around 1 kilometer, let's say that the peripheral area is getting raining, but then when you go to the half kilometer away, people do say that there is no rain. So it's very very versatile and critical. So that is what is called the cloud bursting and climate change. In fact, especially for the aerospace applications, defense applications, it is one of very 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 important. And in order to maintain the susceptibility for the the space applications as well as for the defense applications. And whatever you do it, and all energy sustainability is a more important thing. Whatever we try to do, the technology will try to the sustain the energy for the human life. Whether you call it as a climate change, or the weather prediction, or a cloud bursting, or heat transfer, or IoT of things, or smart farming, or mechanical seals, machine tool waste, and many more areas. Especially these days, you see that quantum computing and artificial intelligence and machine learning, deep learning, many more areas. So therefore, energy sustainability is one of the important things, and it is very nice that they have clubbed up with the sustainable energy and climate change, and which is very very important topic when it comes to the mathematicians and computer science and physicists and atmospheric scientists are concerned. My talk will be going in different directions. Like I would be giving different examples in mathematics, how they would be climate change would do takes place, and also do take up the statistical applications, and ultimately we will end up with artificial intelligence and machine learning, how they would be useful in scientific applications for the sustainable energy and so on and so forth. Well, when it comes to the overview, mathematical foundations of energy systems and climate change, all of you knowing very well, there would be when I talk about the climate, when I talk about the atmospheric sciences, when I talk about the weather prediction, you will find out the equation of continuity, equation of linear momentum in x direction, linear momentum in y direction, linear momentum in z direction, and there would be a heat transfer equation. And these are the four equations which I do get it quite often, along with the continuity equation. So the unknowns are actually, as you see, that there would be velocities, there would be pressure, there would be a temperature, and there would be a dispersion, and if you take it up into the concentration and so on and so forth. So the mathematical foundations of these equations are very, very important, and unless you do understand the the physics behind the mathematical equations, so you will not be able to understand how do you find out the numerical approximation to these the derivable partial differential equations, along with some initial and boundary conditions and so on and so forth. Well, you require the concept of the some extent linear algebra is also required, and how the coordinate system takes place in the Cartesian frame of reference, and also cylindrical frame of reference, and also you do get what we call this the Cartesian frame of reference. For example, when you're talking about the blunt bodies, cylindrical bodies, the Cartesian frame of reference no more it works. Then you need to transform the Cartesian frame into a cylindrical or spherical coordinate system. Accordingly, the governing equations and the properties would do change. Then numerical methods for solving energy and climate equations very, very important. All of you knowing very well, we are trying to find out the best approximations by using the standard numerical procedures, which are actually iterative procedures, implicit numerical techniques, and all iterative procedures. Because you start with some initial approximation and you try to trigger it in the course of time to make into the better approximations. As the runs are keep on going on, you try to make in a sense that the error should not get propagate. So that's how you do the numerical modeling for the equations of the Navier-Stokes equations, continuity equation, momentum equation, which are actually climate modeling do face a vital role. There are several project-based approaches with real world applications. So like cloud bursting, and all of you knowing very well, recently the Gujarat tragedy, very well, the flight, it could not able to develop the enough thrust. So therefore, when the thrust is not able to develop whatever is being required, the moment of the flight or vehicle will not take place. Hence, the moment of the vehicle will not take place, there would be a collapse in the ground level itself. So the higher the thrust, the better will be the vehicle moment. That is the basic fundamental of the aerospace dynamics, which we use it. And same thing do happen in the climate modeling also. So the bubbles, wherever the cloud, they do form it, they bombard each other, and they try to, the accelerate and that particular geographical area. Then you do say that the particular area has got rain. Integration of sustainable energy and climate change mitigation is very, very important topic. In fact, it's one of the very, very thrust area. Government of India has made several projects and several openings in Ministry of Earth Sciences and Department of Science and Technology, so on and so forth. Well, in this talk, I will try to inculcate some of the ideas. After completing this presentation, you will be able to see that apply the matrix methods to energy systems and optimization problems. How actually you would able to optimize these problems, not just simply trying to solve the old problem in the old day. It's not that. I try to optimize the problem in a such way that the energy would be conserved and the energy sustainability should be taken into consideration. And in the course of time, you do get what you call eigenvalues analysis for stability assessment in power systems. When you talk about the stability, there would be a properties what we call consistency, stability, and convergence. So consistency is that how the physical model will be coped up with the derivable partial differential equations when you do the Taylor series expansion, and the truncation error should not get propagated. And similarly, when you talk about the stability conditions, you have got a dependent variable, you have got an independent variable. Small change in the dependent variable will have a equal or enormous changes in the independent variables. That's where the stability comes into the picture. And after having done this, the what do you call this, the stability and consistency, you do get into what you call a convergent solution. And consistency and stability are the prerequisite to a scheme become a convergent solution, so that you would get a better approximations. And we try to develop optimization algorithms for renewable energy systems, and renewable energy systems will become a very vital role for sustainability of human being and more economic point of view. Analyze integrated energy climate systems using computational methods. So the basic idea is, you have got some physical problem, you try to model by using the partial differential equations, and then you try to trigger it so that you get a better approximations. Well, when it comes to the sorry, when it comes to the linear fundamentals, which you see that linear algebra in energy systems, there will be key applications: power flow analysis using admittance matrices. No, the matrix elements, I do represent the each, the energy of the each coefficient as a matrix elements, right? The storage of energy is optimization using a linear programming, that is a minimization problem or a maximization problem. Wind farm layout optimization using matrix formulations. So therefore, once you do form numbers, these numbers are actually from the admitted matrices, and they do come up as a storage elements. Grid stability analysis using eigenvalue methods. So therefore, ultimately my job is to find a system Ax is equal to lambda x, where x is unknowns, A is the coefficient matrix, and lambda is the scalar. And these lambda scalars are actually will give the stability of the systems, whether it is the conservable system or not. Well, that's how the mathematics and physics, computer science is being clubbed up with this, the sustainable energy and climate change. Well, if you look at the fundamental matrix equations, the power system is represented by YV is equal to I. So that means Y, we call it as the admitted matrix, and V is the voltage vector. The identity matrix. So if the product of two matrices V into Y is I, then we say that the two matrices V and Y are invertible matrices. So once they are invertible, in the sense that when it comes to the physical point of view, each can be derived from the other and vice versa. That is the basic idea of the Vy is equal to I. Well, there would be what we call the matrix formulations for power networks. When we talk about this, for a power network, you see that there will be the power, there would be a discrete points at a discrete locations. The moment when we have a discrete points, we will write it as a summation. That is why ii is nothing but summation j not equal to I yij plus the shunt. The shunt is the additional. When n becomes larger and larger, the shunt will become slower and slower, and it will be negligible at a larger stage. So therefore, yij is nothing but minus yij, where small yij is the individual factorizations, where capital Yj is the assembly of all the individual factorizations. Similarly, when the power flow equations, when you talk about the power flow equations, where the energy is getting generated, right? Energy is getting generated. So there will be 2 points, Pi and Qi, and Pi is the angle subtended with the coordinate axis in terms of theta, and as well as this cos theta, and as well as sin theta. So if you write this eigenvalue problem in the renewable energy systems, then we can write it as a small signal stability analysis. We will write it as a linear system as x dot is equal to ax plus bu. So the dot is nothing but the derivative with respect to time variable. So essentially it is with respect to time. That is a dynamical system. So dx by dt is nothing but ax plus bu. Well, the eigenvalues of the matrix A determined by the stability, it becomes the essential criteria is that the the determinant of a minus lambda is equal to 0. So therefore, as long as the determinant a minus lambda I happens to be 0, you would be able to get a stabilized systems. You can find out the yeah. So yeah, please mute all of you. Yeah, so you can find out the applications in a wind turbine blades vibration analysis. That's one of the very important thing where the many machineries do takes place, power system oscillation modes, how actually the power system takes into place, microgrid stability assessment you can find out in the real life systems. And when you talk about these approximations, like the climate change, there would be these approximations can be obtained by using what we call it differential equations. As you know, the differential equations you do solve by using a standard procedures, and there are some ordinary differential equations, there are some partial differential equations, because getting ordinary differential equations is very rare, because you will have more than one independent variable. The number of independent variables are not one, there are many more. So therefore, obviously, you will be representing by using a partial differential equations. So to approximate these partial differential equations, you will have a finite difference methods. That's one of the finite difference method is the sophisticated, foremost, and more powerful method, and to solve the partial differential equations over a structured domain for reasonably good linear and nonlinear problems. What is the nonlinearity? Nonlinearity is the unwanted properties which does come abruptly. Their system will become a what you call oscillations, and it will have a numerical oscillations. So therefore, we use finite difference methods. Also, we use the Ranjikuta method. Ranjikuta method is a single step method where you would be able to find out the approximate solutions to the given differential equations. Other one is what we call implicit integration. This is also being used. Implicit integration, instead of solving the differential equations, you do solve the integral equations. Then the fourth one is what is called a spectral methods approach. Spectral methods approach is also very, very important method where the domain becomes an arbitrary domain. Because you're working on the control volume approach, so therefore domain will be no longer a structured, it will have a abrupt changes from time to time, right? For example, you see the wind, it is abrupt. When you calculate the pressures, densities, vapors, etc. in a particular geographical area, it may vary much different from one place to another place. That's how the cloud formation takes place. Well, not just only doing these approximations, but other hand, you need to do what you call optimization. To do the optimization, you will have a linear programming. The variables subjected to some constraints will be able to make it up the linear programming. Or there would be a quadratic programming where the variables will have the not just linear, it may be a quadratic. Or there will be algorithm called genetic algorithm, or there will be a particle swarm optimization. These are all different techniques how optimization process can be carried out, and in fact these are all called post-processing applications. Okay, in the pre-processing, what we do is we'll try to set up the model, we'll try to see that what are the parameters associated with that, and then in the processing we adopt the methodology, and post-processing we'll try to visualize and see that how we could able to interpret depending on the physics of the problem. Well, when it comes to the matrices, right, matrix computation also very, very important, because each element, the property, you will write in terms of some elements. These elements will be represented in matrices. That is what is called LU decomposition. So when you write the elements of the matrices, and ultimate goal is that you need to solve these matrices. So many times it becomes a cumbersome or difficult to solve those matrices, and we'll try to factorize these matrices. One of the way of factorization is the LU decomposition of the matrix. And there is another algorithm called QR algorithm for eigenvalue problems, how we could able to do it. Then third one is what is called singular value decomposition. You can find out singular value decomposition in many applications as the image processing, where the noise removal is the main course of action in order to get the better inputs. Well, there will be the differential equations can be used in the climate modeling. For example, if you look at into the energy balance model, C into dt by dt. C is the concentration, or you can call it as a heat capacity in other sense, or T is the temperature associated with that. Q is the solar radiation. Alpha is the albedo, some non-dimensional quantity. F is the greenhouse forcing vector. So you can write C times of dt by dt is nothing but Q into 1 minus alpha minus sigma into T power 4. Fourth power of the temperature plus F, where F is the greenhouse forcing term. And similarly, when you write in terms of atmospheric dynamics, that is the primitive equations in vector form, you write dou U by dou T plus U dot del U is equal to minus del P plus F, where F is the forcing term, minus del P is the pressure gradient. Minus sign is taken because the pressure is in the anti-clockwise direction, and U dot del U is the convection terms, and dou U by dou T is the unsteady case. And there will be what we call energy balance models. There are zero dimensional models, that is global average temperature evolution. You can write that C into dt by dt is S naught times of 1 minus alpha, where S naught is the constant, alpha is the thermal diffusivity in particular cases. Where one dimensional model, if you take it latitude, the latitudinal temperature distribution, it becomes C dt by dt is equal to Sy into 1 minus alpha y, and plus d times of d square t by dt square. So the term d square t by dt square is basically meant for the diffusion term. Well, the diffusion will be due to dispersion in the particles. So when you have a particles, there will be a change in the amplitude, there will be a change in the wavelengths. Okay, there will be dispersion and there will be dissipation. Well, not just only the usual way of doing it, there would be a statistical methods for climate change also quite often in the literature being available. One is what is called principal component analysis. That is what is called PCA. Very, very important when you talk about the artificial intelligence and machine learning PCA analysis. Decompose the climate field X. X is equal to U into sigma V transpose, where sigma is the matrix where the diagonal elements are non-zero, rest of the elements are zeros. Where U contains spatial patterns and V contains the temporal patterns. So spatial patterns, temporal patterns. This is the most basic standard equation for the principal component analysis, which we use it in artificial intelligence and machine learning approaches. The other one is what is called regression analysis. There also we use what we call temperature trend estimates. So you can write T of T is equal to beta naught plus beta 1 T plus epsilon T, where epsilon is the small quantity which is a function of time. Beta 1 represents the what you call the trend coefficients. And there are other methods also people keep on using it on various occasions. That is called Monte Carlo methods. So Monte Carlo method says it is called parameter uncertainty in energy models. So you can write E of y is nothing but integral of f of x plus p of x dx. That is approximately equivalent to 1 by n times of summation I is equal to 1 to n fxi, where xi are the random samples having the probability distribution pxi, and sensitivity analysis is sensitivity coefficient SI is equal to dou y dou xi upon yi. Morris method for solving the screening equations. Yeah, so there will be what we call the Monte Carlo simulations. And Monte Carlo simulations are the one of the very familiar methods whenever you get what you call uncertainty. So that is parameter uncertainty in energy models. That is C of y is equal to integral f of x p of x dx. Then you get 1 by n into summation I is equal to 1 to n f x I, where n is the number of the parameters which we use it. Like for example, if you have a climate change, density, pressures, velocities, okay, these are some of the parameters which you use it. Where xi is the random sample from probability distribution. For example, if you take samples, different samples, and not just only samples are huge number. Let's say that n is equal to the xi, x1, x2, x3 are, let's say, 1 lakh. So that means the huge number of data you're using. That's why we need to use Monte Carlo simulations. Another method is what is called sensitivity analysis. Sensitivity coefficient is, we write it as SI is equal to d dy upon dxi, xi upon the omega, the y. That is Boris method for screening the variables. There will be another optimization problem called the framework, other one which we use. General optimization problem is, that is minimization of. Then we subject to the constraints gi of x is equal less than or equal to 0, hj of x is equal to 0 for j is equal to 1 to p, x lies between xl to x of u. So therefore, energy system applications you will have it. Minimization of the cost of x is equal to C transpose x, and power balance is summation of P generation, that is summation P load, because discrete points you are using it. So therefore, we use always the summation. And the capacity limits anyway, P lies between P1 to P2. Well, the again very important thing which you come across is the very important thing is the data requirements and source files. Well, there will be a climate data, that is the temperature, that is which we call it as a real analysis, NCEP. So this is the some organization there, they provide the nuclear center for energy physics. That's one organization. There will be what you call precipitation functions, that is National Atmospheric Research Laboratory. This is the organization. For wind, similarly, that is the government of India has set up in Dehradun, that is the wind systems. Similarly, solar radiation also set up in the Uttarakhand state. These are some of the organizations where actually you get the real-time data for the climate modeling. And energy data, there will be a power demand, that is the Power Grid Corporation of India, we can find out. Generation capacity in terms of the EIA and ARENA. Transmission networks, that is how it is transmitted. Economic data, LOCS databases, and so on and so forth. Well, when it comes to the computational tools and software, in order to evaluate all these things, not just in-house codes you will be developing, but also you can use what you call a MATLAB. All of you are very familiar. You can do the MATLAB, or you can do Octava, or you can use a Python, that is NumPy. NumPy is one of the library, and SciPy is another library. Other you can use Julia, that is also one of the programming language, or you can use R programming language, or olden days we used to have a Fortran and C++ programming languages. And there are some specialized software systems, that is Power World, that is Power Systems Energy Studies, SAM, that's also renewable energy systems, GAMS, that is optimization models. Then there's a climate data operations. These are some of the optimization being available. So when you do this sequential computation, if you are unable to get the proper data, you can also use the tools called high performance computing tools. That is what is called MPI, that is message processing information for parallel processing, or graphical processing unit computing with compute united device architecture, CUDA, or cloud computing platforms. That is all of you as knowing very well, cloud platforms we want to work it. Or else we can use distributed computing framework, how the things would work out from one to another. There will be a mathematical libraries, that is BLAS or LAPAC for linear algebra, Intel MKL for optimized operations, FFTW for Fourier transforms, and optimization toolboxes also one would be using it. Validation and verification methods, there will be model validation, cross validation with statistical significances test. We use it, that is testing of hypothesis, 95% level of significance, 5% level of significance, and so on and so forth. There will be verification matrices, metrics we use it, that is what is called RMS, that is root mean square errors, and that is nothing but 1 by 1 summation and is equal to 1 to n yi minus yi cap. So yi cap is approximation, yi is the initial, and square of this will give you root mean square error. Or we can also use mean absolute percentage error, that will give you more insight into the problem which we do consider. Also, when you talk about the approximations, we also need to worry about the errors. What would be the state of the errors? So if you do the state of the errors, we can actually replace the governing partial differential equation by finite difference equations by using the Taylor series expansion. So when you take into df by dx, for example, f is a property, or let's say a very property, then df by dx would be approximated as f of x plus h minus fx by h, where h is the spacing in the x coordinate system. So that can be written as df by dx plus h by 2 times of d square f by dx square plus order of the terms of h square. So h is the spacing which we assume to be very small, h square is too small, h cube is etc. h cube and higher powers are diminishingly small. So therefore we can write the truncation error as tau is equal to h by 2 times of d square f by dx of 2. So therefore round off error is, total error in numerical computation is, E total error is nothing but, that is E truncation error plus E round off error, and optimal step size minimal error will become a very, very interesting topic. Sometimes we also use what we call von Neumann stability analysis for convergence. How actually the values are getting converged. So we use what we call von Neumann stability analysis. For a different scheme, un plus 1j is nothing but g of unj. Then we call it as the amplification factor. So if the amplification factor is the term which will actually decide the stability of the schemes, g is equal to 1 plus r times of cos of xi minus 1 or minus of ir times of sin of xi stability condition, that is mod of j is less than or equal to 1 for all xi. So current Fisher-Levy condition is, for explicit schemes, delta t less than or equal to delta x upon, that is mod of u, where u is the wave speed. This ensures numerical stability and time dependent partial differential equations. Convergence rate is, for iterative schemes and all, norm of xk plus 1 minus x star will be less than or equal to xi into xk minus x star, where rho is less than 1 is the convergence rate. The spectral radius, you can write it as, system is stable if spectral radius rho of a is equal to less than 1, then the stability will become a much more stable condition. So what is the spectral radius? Spectral radius is nothing but maximum of I mod of lambda I, where A is the matrix, the eigenvalue associated with that matrix, then we can compute the spectral radius for the stability of the systems. So we also use, there are several softwares are available. One of the software is BLASIS, that is called Basic Linear Algebra Subprograms. Then there is a LAPACK, that is package. There is Intel MKL, that is Math Kernel Library, and also for the optimization we use either CPLEX, linear or quadratic programming, or GROBY, mathematical optimization, or NLOPT, that is nonlinear optimization techniques. So there are to solve the ODEs and PDEs, there are other softwares also being available. And one of the important thing is that how actually solar energy in mathematics can be considered under direct normal irradiations. If you look at it, that it would be L naught times of e power minus tau b into cos of theta z, where L naught is the extraterrestrial irradiance and T is atmospheric optical radiance. See that why I was talking about this radical model is, if you go to the hill areas, right? For example, Uttarakhand, if you go to hill areas, the atmospheric, the properties are quite often they do change when it comes to the non-hill areas. Okay. For example, if you are in Telangana, and that is actually not the hill area, but then it is the upper side of the plateaus. So in that case also the atmospheric conditions are quite abrupt. For example, if you talk into the Jharkhand, here the atmospheric conditions are much more abrupt. For half an hour back, you do get a sunlight, and the next half an hour immediately it rains heavily, and after half an hour you see that its sunlight is too high. So the changes becomes very, very frequent depending on the geographical area. Well, there will be a photovoltaic cell mathematical models also being available. How actually the sunlight would be affecting the photo effects, that is the current voltage relationship that automatically it develops and it try to trigger into the the voltage models. That's what we call it as a sparks, in the atmospheric sparks. Well, the linear programming formulation, it becomes what is the maximum power output, that is maximum of C transpose X, that is 7, or in the given equation 7, and if you subject it to the conditions that Ax less than or equal to B and X is greater than or equal to B, where X represents panel orientations and C represents power coefficients, and which we call it as a shading factor matrix CS. Well, there will be what we call single axis solar tracking methods. Minimize incident angle by setting d theta by dB is equal to 0. So essentially theta is a function of, and it's alpha, where beta will become the relevant. So this leads to the optimal tilt angle. Tan of beta is equal to sine of omega upon tan of phi minus delta cos of omega, where omega is the hour angle and theta phi is the latitude and delta is the declination, how actually it declines. There would be two angles, that is called azimuthal angle, and there will be elevation angle, right? So which we call it as a, whenever you talk about the thrust making in the flights or aeroplanes or rocket, etc., we try to calculate the azimuthal angle, that is elevation angle and azimuthal angle, with respect to the height and as well as width. And there will be what we call the iterative procedures which we use there, where actually the numerical approximations are very, very important. Then we use what we call a Newton-Raphson method. Newton-Raphson method, why we use is, it is nothing but to find the root of the equation where actually the tangent, it touches the x-axis at more than one point. Probably if it touches at more than one point, you will have many more roots. The best route you need to find out by computing in the different iterative procedures. There will be interference clear sky model, that is also very, very important in atmospheric models. That is, we try to see that the air mass factor we compute it, linkage turbidity factor we compute it, moisture we compute it, and you find out applications in baseline for solar resource assessments, performance ratio calculations, and clear sky index for the flight mechanics and weather predictions and launching of the vehicles. Because the abruptness, because of abruptness, there would be what we call statistical properties. Then we use what we call a stochastic weather modeling. So there will be what we call Marconian chains for weather states. Marconian chains is nothing but do arrive in the what we call the poison, the exponential fashion, and the service will be in the exponential fashion. Service will be in the more and more oriented. Then that the process is what we call a Marconian chain process. That means customer enter into the system in the bigger number, and the service also will be controlled. Then that's the process is what we call a Marconian chain process, which we do it in the cloud formation. Well, there will be a systems what we call perturbed and observed method. Pk compare with previous powers P of k minus 1. So since it is an iterative process, just not that don't need to worry what would happen to the P minus 2 rotation. P minus 2 rotation is different. P rotation, P minus 1 rotation is different. P rotation is different. So ultimately we'll be able to club it up how actually we are getting the what you call compare with previous results in order to get the better voltages. There will be what we call the solar form optimization theory for the objective function in order to get the sustainable energy. Maximum annual energy will become maximum of summation I is equal to 1 to n, summation I is equal to 1 to t, PIT 1 minus S of IT, where PIT is the power from the panel I at time t, and ST is the shading factor. As we see that shading is also very, very important, how actually to be able to cope up. So we also people do use different algorithms, not just CFD code, not just that the Python code and things like that. They can use genetic algorithm also, that is initialization population of layouts, that is while not converging to do, then evaluate the fitness, energy yield for each layout. Then select parents based on fitness, apply crossover and mutation, replace worst individuals with offspring, and then you complete this program so that you could able to begin to find out how actually the genetic algorithm can be used for a particular case. Similarly, when you talk about the large scale solar installations, like the government of India is giving so much population everywhere, and every government buildings, any subsidies in the colonies or gated communities, and they wanted to have a solar base panels to minimize the energy and to make yourself by using what you call sunlight, by using the tunnels, and that's very, very important thing. In fact, all of us would be cooperating for the government of India to do that. There will be a what you call net pressure economic analysis for sure for the solar systems, and net pressure how much it takes. In fact, pressure is known, velocities are known, then easily you could able to find out a system which will give you levelized cost of energy, where this is nothing but summation T is equal to 1 to N, that is Li plus Mf plus C, and these LT, MP, FF are the investments and maintenance or the fuel cost, so that you could able to find out a best possible way of doing it. Similarly, there are, if you go to the Indian continent, climate change, Himachal Pradesh and Haryana, you'll find out wide power equations. There are wind power tunnels, Bakran angle project over it. There are many more. In fact, we have not gone to that extent still because the coal availability is there. Still, we believe that the coal is being available, so we wanted to do the thermal energy by coals. But it is not necessarily true, and there are wind power etc. equations in other parts of the country. So power extracted from the wind, that P is equal to half of rho into AV square Cp, where D is the density. You know very well density is nothing but mass by volume. The higher the volume, the lesser will be the density, and vice versa. So when it becomes sharper and narrow, there will be a huge wind will be stored, so that it will be enabling the vehicle to be more go on faster and faster. So therefore, A is the rotor swept area, and W is the wind speed, and Cp is the power coefficient, and so on and so forth. Force analysis is axial force on blade moment element dfx is nothing but 1 by 2 rho v square, that is C1 of sin phi, C2 of sin phi, and so on and so forth. We can use global coordinate system as well as the local coordinate system in order to find out the induced values. Well, there will be a, what you call the momentum theory also being one of the very important thing which one can use it, that is induction factorizations. Axial induction factorization, we use momentum balance, we use it, and iterative schemes also we use it. So what are the schemes we are familiar? We are familiar about iterative schemes. So iterative schemes are nothing but we start some initial approximations, we try to trigger it, and in the course of time, this initial triggering approximation should become a better approximations. That is the process how we could able to do it in order to get the best approximations. There are other schemes like boundary element method, requires iteration between blade element and momentum equations and the convergence equations. Well, there will be not just only in applications in fluid mechanics or computational fluid dynamics. There are applications you can find out in structural dynamics. So when you talk about structural dynamics, epsilon into, that is nothing but epsilon into m into. So there will be what we call the equation of motions and x double dot. X double dot in the sense that is a derivative with respect to x twice, then which we call it as the momentum equations. And cx dot is the c is the concentrations, and x dot is the time derivative. Kx is equal to ft, and f is the force vector function of time. So this leads to the eigenvalue problem, that is k minus omega square of m acting on phi is equal to 0. Phi is any of the variables. There will be a blade vibration models, first flap wise models, that is f1 is equal to up to 0.7 hertz, and first degree wise f2 is equal to 1.1 hertz. Similarly, torsional models, that is 3.5 hertz. Torsional models are the best models for a machineries and even climate change, because they could able to give a wind effect. So, well, the weather prediction and the forecasting can be done by using what you call primitive variable approach. So, in the primitive variable approach, that is dou u by del t plus v dot over is equal to minus del p into f, and therefore you could able to write it as, so you could able to write it as dou theta by dou t is equal to u dot del theta is equal to mu, and del dot v is equal to 0. Del dot v is equal to 0 because the flow becomes a what do you call a continuity, therefore this condition is to be automatically satisfied. Similarly, when you talk about the boundary layer approximations, there will be what you call mono obscure sustainability, and du by dt is equal to, that is phi upon k z into times of, that is z comma l. So z comma l are actually the initial values, and l is the length. Well, there will be the Weevil distribution also. We use it not just only a statistical properties of first moment, second moment, third moment, etc. So Weevil distribution also we use it because ultimately we wanted to be responsible for the principal component analysis (PCA). So that is very very important, where you can find out a lot of applications. And the wind speed probability density is f of v. We can write like this, where k is the shape parameter and c is a scale parameters. Well, there are some the power density equations which we can written as integral 1 or omega, that is 1 or 2 omega into. So we can do it as a k is a shape parameter and c is a scale parameter, and power density can be written in terms of the vectors, and then because it is going to be infinitely, so therefore it is 0 to infinity v cube f v, and that can be simplified to the equation given here, WPED.